Are you getting anything? Now? Okay. All right. Okay, so is it recording? Okay. So we'll start with a solution to kernel SVM. So this solution looks like so this is simply obtained by solving the Lagrangian of the kernel SVM procedure, and I can write it in terms of the slack variables as in terms of the dual variables as okay. So K is the kernel function that I'm using in kernel SVM. Okay, and E here is a vector of ones. Okay. All right. So let's see how I'm defining this function g of k. This is simply defined in terms of the kernel function. Okay. So I'll take given k, this is going to be a matrix, and the procedure that I'm going to present, the semi-definite program that I'll derive learns this kernel k. Namely, it learns the gram matrix of the kernel. Okay. So I'll start with a training set. So I'll have n training samples. And a test set. And I'll have NT training samples. Sorry, so these are labeled samples and these are unlabeled samples. So I'm only getting the x's here, not the y's. And the idea is that when I learn the matrix K, it will have several components. So first of all, it will have a submatrix that represents the gram matrix for the training samples. Then some mixed submatrix. And then a portion that will contain the evaluations for the test samples. Okay. All right. So what we're going to do is we'll optimize over this training submatrix, and then we'll learn the mixed component and the test component. Okay. So use this generalized performance measure based on our omega. Okay, so this function is convex in terms of k. And the constraints are just the constraints that we get from the kernel SVM Lagrangian. Okay. Yes. K is a matrix. Yeah. So K is the. Yeah. Yes. K is this one. Okay. Yeah. Okay. So writing this this procedure. So writing the procedure in terms of K, we'll get something like. We'll need to minimize over like the set of a set of matrices K. So this is a restriction. So this contains like a restricted set of kernel matrices that I'm considering, and this of course. Yeah. That's just, well, we don't know that necessarily. So we'll solve. Yes, but we'll solve for the training samples first. So this is for some matrix or some function K. So this is K, the kernel function, basically. You know, there exists some value. It's just that I don't necessarily have it here. So I'm going to write G of K train, and I'll assume that this is known.
Okay, so on the right-hand side,
Yes.
The K is the same as K train.
Well, so the K is generic. I'll explain later. Yeah, we'll solve it in terms of for K train first, and then we'll do some other. We'll just put some additional constraints to get K, like the mixed component. Okay. So yeah, basically yeah. For now, let's just assume that we're solving to get K train. Okay. Okay, so so just this procedure for some matrix K, we're going to optimize it over a class of kernel matrices, and this kappa is of course so this is a space. It's subset of the positive semi-definite cone. Okay. And we're going to minimize over K train such that okay. So we're going to minimize with a trace constraint. And now what we get is
the ground matrix in the ANC.
yeah.
So then how can the trace be, I mean, so you mean all the eigenvalues are 0?
Sorry, no, it's a constant. It's not 0. Okay, it's a constant that's greater than 0. Yeah, good spot. Sorry about that. Okay, so all right, so what we'll have, we'll have a minimum over K, maximize over alpha out of the expression we wrote, which is 2 alpha E minus. So just substitute like K train. Okay. and it's subject to the same constraints I wrote there. Alpha is between 0 and C. Alpha T Y is 0, and trace of K is supposed to be C. So we're gonna like have this procedure. So now assume that K train is positive definite, then it results that G of K train is also positive definite, which means that G of K train plus tau I n train is also positive definite. Okay, and because this procedure is convex in K, we can simply like use a change of variable and write it as minimum over T under the constraints that so I'm just going to replace the entire objective with a single variable. Okay, and then I'll write the Lagrangian for this. So the Lagrangian looks something like introducing eta and lambda as dual variables. Oh, and delta is also a dual variable. And yeah, lambdas, of course, is scalar, and these dual variables are have n train, are vectors of size n train. Okay, so yeah. That was just so I could. I think that's just so I can. So I'll show later. It's just to put the objective under one variable, and so this constraint I'll rewrite it as something else. Okay. So you'll see. Yeah, you can do that. It's fine. I mean, as long as it's.
So the point is to make it equivalent to the one.
Yeah. Right. Oh, okay. Okay. Is it? Is it better now? Okay. So I'm gonna. Okay. So I guess I'll continue this. I'm not sure how to move this up, but you still won't be able to see them, right? Oh, okay. Yeah, maybe I'll do that.
I'm not able to understand why we would put a constraint over trace. I mean, what would we get from that?
Like a bound on the eigenvalues, I guess.
How
Maybe
would
you should like this avoid get a trivial k, like k equals to 0.
But then you can put a inequality, right? That greater than 0, right? But why would you put a constant there?
You can also have this to be greater than c because trace is an affine function. So we can either ignore it equals to 0 equal to or greater. But I don't know.
So I always thought it was it was for like to reduce overfitting. I always understood it as that, but I guess what you saying it makes sense also.
Yeah, I think overfitting makes sense to me.
Is that?
I would say.
Also, is this c the same c as the constraint on the alpha? Alpha is
No. That's capital C. So that's the C from. So that is the slack variable from the SVM. And this C is some other. Yeah, sorry. So that's supposed to be this is supposed to be little c, and that's supposed to be just from the SVM.
If the overfitting was the thing, then don't we say that SVM is very not very prone to overfitting in the to begin with itself because they have.
But we're not just doing the SVM, so we're doing SVM without knowing the kernel, right? So when I say overfitting, I mean overfitting in the kernel matrix, right? Okay, that's my intuition of it. Anyway.
Well, if you take k equals to 0, you get a trivial solution on both the final and 0.
If you take k equals to 0.
You do not have to put something on both. There's nothing.
Yeah. Right, but why exactly equal to c as opposed to greater than c, right?
I guess it gives you the same solution because if it's greater than c, then it will always be c.
Why would it always be c?
Because reducing the size of the matrix k reduces the objective function value. Yeah, maybe you continue. I didn't read the paper, so my comment.
Okay, so I mean, does it always?
Yeah, it looks like
From the definition. Yeah. Yeah, I guess you're right. It should be. Then it's just to avoid a trivial solution. Okay, so I guess. I guess so we can move on and write the dual solution we obtain for W. It's minimum over these dual variables, the maximum over alpha of that look function. Okay, so because we have that, because of this positive definiteness, then we know that at the optimum, so alpha at the optimum will be something like which putting back in that optimization, we get the W is simply this. Okay, and we're just going to call this like this complicated thing W of W of eta, delta, and lambda. Okay. All right, so we got, so after getting the solution for alpha, we got the solution for W, for the weights. And whoa, okay. So now all we have to do is write this in terms of t. So we know that this is smaller or equal to t if and only if for every lambda, for every eta, delta, and lambda, W is smaller than t. Okay, so if for every combination of these, this W is smaller than t, then this omega will be smaller or equal to t because it's the result of a minimization. Okay, this is equivalent to the following. So we'll define a matrix. So this is equivalent to M of K trace tau, and all of these variables we've introduced being positive semi-definite. And this matrix M is defined as by just looking at W. Okay, so this matrix needs to be positive semi-definite for this thing to hold, which means we can write the entire optimization procedure using just this matrix. So we can write the procedure. So that thing that I called star over on the other whiteboard, we can rewrite it in terms of T as like minimum over K T lambda delta and eta T, such that we have the trace constraint, and K needs to be in some subset of the positive semi-definite cone. This matrix that we just defined is positive semi-definite. Okay. Okay, now what we notice here is that this particular procedure, so this is how we learn the kernel matrix. If we only cared about this testing, the training matrix, okay? This is just an SDP in standard form, okay? However, we'll need to also worry about the test part of the matrix. So let's say if you look at the form of K over there, if KT is 0, this thing is minimized for some K train, right? So we'll need to introduce some constraints over the test and mixed blocks in order for this to make sense. Guess. Where should I? Should I just write this on the other? Or, yeah, just to leave this on. Okay, so now we'll have to be more specific about the set of matrices we're considering. So consider K to be the conic hull of some M matrices K1 to Km. Yeah, so these are known kernel matrices that we're considering. And we're intersecting this with the set of positive semi-definite matrices. And we're going to have that the matrices K that we're considering can be written as conic combinations of the kernel matrices. So to that SDP, we need to add the following constraints. So we're going to have that we're going to replace the trace of K with like trace of, so we're going to replace the optimization over K with an optimization over the mu i's, which give us K. So first we're going to have the trace of this conic combination.
So the assumption is that the training K will be like the base K by the.
Yeah. No. So these are just some. So in order to actually get to the test and mixed blocks, we'll need to make more assumptions about the form that the kernel matrix takes. And we're only considering matrices within the space, because otherwise we can, those blocks can just be zero, right?
So
It doesn't
then
affect our
in terms
precision.
of data, does it mean that there is correlation between the data in training set and the data in test set, right?
I mean, there is, you assume, it doesn't mean that there's correlation necessarily.
Because if you are assuming that you will get the test kernel,
These aren't the training kernels or anything. These are just a set of M kernels that I'm considering. They're not the result of that procedure. They're just, Yushan, does this make sense?
These K1 to Kn, I believe they're predefined kernels.
Yeah, they're just,
And these like the solution set,
so how do you get these two different kernels?
you can
Oh,
define it to be
some-
kind of spaces of the space of kernels. So it's like taking a conic combination of this thing always give you another kernel.
Yeah, so for now, are these known or unknown?
They are known.
They are
We
known.
want to find the conic combination of these things that is the best.
Yeah, but then how do you define the basis?
so you, I mean, you can just take, you don't necessarily need to define a basis. You can just take M kernel functions that you know are kernel functions. Just whichever.
Like that, if you want to span a different range of like complexity, you can take the m different polynomial kernels with different like order.
So these kernels will be made up of what? The training data, right?
No,
How do
they're
you get
just,
these kernels from?
I mean, you know the
Okay.
function of these kernels, right? You can compute them on both the testing and the training
So
because
we
they're
are
known
not
functions.
getting these kernels like in a gram matrix format or something like that, right?
Yeah, I mean, these are kernel matrices, right? They're the gram matrices of your testing and train data.
Only the training data.
No, both testing and training. Right? So we're just evaluating these kernels because they're known. We can evaluate them on training and test, right? And what we don't know is K. We do know that it's they're conic combinations, right? So we're trying to learn the parameters of the conic combination. Okay, does this make a bit more sense? Okay. All right, so we just replaced the condition. So the condition on the trace of K with a condition on the conic combination, and we'll have that. We'll also use the same for here, except for this matrix we've defined. Except here, I'm only considering the training part when evaluating this matrix that needs to be positive semi-definite. And let me define what KI train means. So KI train will just be the training part of the KI matrix. Okay. All right, so after writing this, we can, so now we can rewrite this whole thing as a QCQP. I'll just write it down. these Ri things are just the traces of the kernel functions. So this QCQP formulation holds only when I actually have conic combinations. Otherwise, it's just an SDP. And clearly here, G of Ki train is this diagonal of the output vector. This comes from the definition of G. Okay, so what did we do? So we started with an optimization over the kernel matrix derived from kernel SVM. Okay, we first just wrote the procedure in order to optimize over the training function, the training part of the kernel matrix, and then we added a constraint on the set of matrices we are considering, such that we can also estimate the test and mixed blocks of the kernel matrix. Okay, that's it. And under these conditions, we actually get a QCQP rather than an SDP for this particular class of kernels. Okay. Okay. Now I'm going to talk about hyperkernels. So Alex said we should discuss that, and I think there's some time left. Okay. So hyperkernels are basically kernels over the space of kernel itself. So the regularization is imposed on its associated hyper-RKHS. This basically allows the parameterization of kernel classes without overfitting. So Alex claims that the procedure these guys introduced that I just presented now overfits severely. And for that, he used like a quality functional, which is equivalent to the empirical risk functional, with some additional constraint to prevent overfitting. Okay, so a quality functional looks like this. We're going to use this notation. And it's only called a quality function if it depends only on K via K of xi, xj for all our samples. Okay. This basically, this quality functional just specifies how well matched the kernel is with the data. Okay. So to obtain an error bound on this, we have to, so I'm not going to go into that, but what we would need is a concentration inequality of these quality functionals and a bound on the deviation of the empirical risk in terms of the quality functional. So let's call this the expectation over x, y of our quality function, empirical quality function. Okay. This is the like the expected value of the expected quality of our kernel K for data that come from distributions X, Y. Okay, so who knows who knows the definition of an RKHS? So I won't have to go through it. Do you guys know what an RKHS is? Okay. Do you guys know the representer theorem? Okay. All right. So now I'm gonna skip through those definitions and just define a hyper RKHS. Yeah, so I'm just going to write it out. So let the set X be a non-empty set, and this is the compounded index set defined using X. Okay, then the hyper RKHS. I guess. So I'm going to use this like under bar notation to mark anything that's hyper. It's just a set of functions K defined on the compounded index set. With, of course, this is the inner product, and you know the norm of K is just basically square root of the self-inner product. Okay. So this is a hyper RKHS if there exists some function K defined on so it'll be a function of basically 4 variables in our sample, such that K is a hyperkernel. And by that, it just means that K has the reproducing property, it spans H, and it's symmetric. So let's write down the reproducing property for hyperkernels. So I'll just use this. Okay. So this just means that any kernel K can be evaluated using a dot product with a hyperkernel. Okay. So any kernel in my space can be evaluated by just taking the inner product, which is equivalent to saying the following. That the product of two hyperkernel evaluations is just the hyperkernel evaluated at the two samples. Okay. Okay. So does everyone kind of understand the where does this reproducing property, like what this reproducing property represents?
The general property for all K.
No. So that's the the reproducing property as written for this space of hyperkernels. So I can evaluate any kernel by performing an inner product with a hyperkernel evaluation. So this is something that's called evaluation. Yuxiang, you can follow that?
You guys don't know the reproducing
Yeah. So this literally is just the reproducing property as written for that space, as written for age. So instead of having vectors here, I have matrices. Like sorry, my functions are so this x bar is going to just be a function of two variables. Okay. So instead of just having one variable, I'll have like a pair here. Okay. Okay. So 2 is k. This k bar spans h. Bar, which means that for all g bar in h bar, there exists xg bar such that that g bar is an evaluation of k bar at xg bar. So for all functions g can be written as evaluations of this hyperkernel. Okay. Also, we have symmetry. So let me just write that down. And these are for all x, y, x, t in my space x. Okay. This just comes from the symmetry of k as a kernel. Okay, and the symmetry of all the k's in H. Okay. Now, let's say x and y is my test and training set. So the regularized quality functional is going to be something like this. Where this, so for some kernel k, I'm going to introduce this regularization penalty in terms of the norm in that RKHS. So this is the norm of k in that RKHS. Okay, and this serves as a penalty. And so the representer theorem for hyper RKHSs says that each minimizer of the quality functional admits a representation of the following form. This is just the representative theorem as applied to this hyper-RKHS. So K will be something like this. You guys said you know the representative theorem, right? Okay. So this is just its equivalent on that hyper-RKHS. For these are just some coefficients, and like this is my sample size. I guess I used n so far, so let's keep consistent. Okay. This is simply shown. So the fact that this is a minimizer of the regularized quality functional is shown by just applying the representer theorem for the like hyper-RKHS. So basically, the solution of the regularized quality functional that we introduced is just a linear combination of hyperkernels of the input data, which means we can find the optimal solution by choosing among a finite number of kernels, even though this optimization is over an infinite space. Okay, I'm just going to move here. So let's write the optimization problems that are specific to this. So this is just the regularized risk functional. So this is minimum over K in my hyper-RKHS. Minimize over F. HK. This is just a regularized risk functional using a loss function L of xi, yi, f of xi. It's just the expectation of that loss. It's 1 over m. And this is my my hypothesis space for f. Okay, so I added the constraint. So this is the constraint that we get from the quality functional, and this is the regularization over the function that I'm trying to estimate. And this, of course, can be written in terms of in terms of the gram matrices of the kernels we're using. So this is going to be something like minimum over b, minimum over alpha, 1 over m, sum of over our samples. Okay, so in this procedure, the alphas are the coefficients of the kernel expansion for f, and the betas are the coefficients of the hyperkernel expansions. Okay, okay. So this is basically the optimization procedure for a hyperkernel, and that's I think that's about it. Do you want to? Okay, do you guys have questions?